Okay, I'm not sure how much of that got cut off, but what we did was we proved that if y1 and y2 are solutions, we proved that this is also a solution. The part about proving that it's the general solution, meaning it covers all possible solutions, that needs to be left to more advanced math classes, because the proof is something that we, at this point, with what we know so far, wouldn't be able to understand. Okay, so the next thing I want to do is talk about how to solve this equation. Okay, so what we're going to do is we're going to look at our general second-order linear homogeneous differential equation that would be in the form of this: y double prime plus a y prime plus by is equal to 0. Now, if you think of your functions, any function y, where you could take a derivative, well, multiply that function by a constant, take a first derivative, multiply it by a constant, and take a second derivative, multiply it by a constant, and somehow have those all cancel out to be 0. Okay, one way that could work is they would all have to be like terms, right? So that you can add them up and different constants can make them cancel out to be 0. I mean, if you have a function like sine x, its derivative would be cosine x, and then its derivative would be negative sine x. You can almost think of the two sine x's canceling, but the cosine wouldn't. If you have a polynomial function, even something simple like x squared, the derivative of x squared would be 2x. The derivative of that would be x. There's no way to cancel out this x squared if neither of these are quadratic. Okay? So really the only function that comes to mind is if you have something like e to the x. Then the derivative would be e to the x, the derivative would be e to the x. Or, more generally speaking, if you have something where y is in the form of e to the kx, or in this case we're going to call it e to the mx. It really could be a constant times e to the mx, but we're going to simplify and call it e to the mx. And then y prime would be me to the mx. Y double prime would be m squared e to the mx. Okay. Now, plugging these in, we're going to plug in this for y. We're going to plug in this one for y prime and this one for y double prime. So we get m squared e to the mx plus a times y prime me to the mx plus b times y. So b e to the mx equal to 0. If you'll notice, each of these terms has an e to the mx. Okay, so let's factor that out. E to the mx times m squared plus a m plus b equal to 0. Now notice this thing can never be 0. So that means this thing must be 0. So we end up with this equation. M squared plus am plus b is equal to 0. And if we can solve for m, we plug m back into here. And this is quadratic, so we should have two solutions. And finding those two solutions, we should be able to, hopefully be able to get two solutions y1 and y2, that are linearly independent. And then we can multiply them both by constants, add them together, and that's going to be our general solution. Okay? Now, remember, this is a simple quadratic. Actually, there's a name for this equation. And notice this equation looks a lot like this equation. It's almost like you replace your y double prime with an m squared, your y prime with an m, and your y with just a 1. Okay? It's kind of interesting how that works. This thing is called the characteristic equation. So if you have your second order differential equation up here, its corresponding characteristic equation looks like this. Okay? 3 things happen when you solve a quadratic. So you could have case 1, m1 and m2 are real and distinct. And if that's the case, your general solution is going to be C1 times, and you're going to plug in M1 for the first one, e to the M1x plus, and then you plug in the second one, have another constant here, e to the m2x. So your two solutions are e to the m1x and e to the m2x. We call those y1 and y2. Okay, so we call that y1 and y2. So if y1 and y2 are linearly independent, and these would be linearly independent if m1 and m2 are different constants, like e to the 3x and e to the 5x. There's no way that you could multiply one by a constant to get the other, so these would be linearly independent. So the general solution would be c1, y1 plus c2, y2. Okay? Your second case is where m1 and m2, well, m1 and m2 are equal, so we can call them both just m. Okay? So they're real and not distinct, non-distinct. This would be m1 is 2 and m2 is 2. Okay, so your solution would be y equals, you want c1 e to the mx. Notice I didn't say m1 because they're both equal to m. Now here's the problem. So you want the other one to be c2 e to the mx also. But the problem is your y1 and your y2 would not be linearly independent. They'd be the same thing. Okay, so that's a problem. So what we have to do is we have to change this second one. Okay? And what we can do, if e to the mx is a solution, there is a proof that proves that x e to the mx is also a solution. I'm not going to go through that proof right now. I don't think our book goes through it. But if e to the mx is a solution, then x e to the mx, meaning a solution to this equation up here, okay, then x e to the mx would also be a solution. And there you've got your y1 and y2 that now are linearly independent. Okay? That satisfies that condition. And the third one is m1 and m2 are complex. Okay? And not just complex, but they contain imaginary solutions. Okay? So maybe m would equal alpha plus or minus beta x. So when you solve this, you'd have to solve it using the quadratic formula. You end up with something imaginary underneath theoretical. So let's say you have 2 plus or minus 3i. Well, let's do an example. Example 2 plus or minus 3i was your solution. Well, alpha would be 2 and beta would be 3. Okay? Then your solution is going to be y equals c1 e to, well, m is going to be your alpha plus, sorry, that's not beta x. It's alpha plus beta I. Thank you. Sorry about that. Okay, it's because you get like 2 plus or minus 3i. So then your alpha would be 2, your beta would be 3. Sorry, that shouldn't have been x, that was an I. So this would be c1 e to the alpha plus beta I times x plus c2 e to the alpha minus beta I times x, okay? And simplifying this, you get c1, and when you distribute this, you get c1 e to the alpha x times e to the beta ix, and then you've got plus c2 e to the alpha x times e to the negative beta ix. Okay? Now, we are going to go off to another page and we're going to simplify this because this we can simplify into something much nicer. Okay? In order to do that, I'm going to keep this here so we can see it. We have to remember our Maclaurin series for e to the x. Okay? So remember that the Maclaurin series for e to the x is equal to 1 plus x squared plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus plus x to the n over n factorial. Okay, so now when we have something like e to the beta ix, okay, well that's going to be equal to 1 plus, and then this, instead of being x, remember this thing is that entire exponent, so we'll call it, I'm going to call it I beta x, and then plus I beta squared over 2, x squared, so plus I beta cubed x cubed over 3 factorial plus I beta to the 4th x to the 4th over 4 factorial plus I beta to the 5th x to the 5th over 5 factorial plus dot dot dot. There's a reason why I'm writing out so many of these terms. Okay, let's simplify. So e to the I beta x is equal to 1 plus I beta x plus, the I squared makes it negative, so minus, we can call this beta squared x squared, so beta x squared over 2, that's really a factorial, right? And then this becomes minus, the I cubed gives you a minus I, so minus I beta, let's do this, minus, that i's not in parentheses, I times beta x cubed over 3 factorial plus I to the 4th is just 1. So now we're going to have beta x to the 4th over 4 factorial plus, and then I to the 5th is just I, so plus I, we've got beta x to the 5th over 5 factorial. And then the next one will be minus dot dot dot. Okay. So e to the I beta x would be equal to, now I'm going to move the ones that have i's in them, I'm going to separate those out. Okay. So I'm going to start with first the ones without the i's. So we've got I, 1 minus beta x squared over 2 factorial plus beta x to the 4th over 4 factorial minus, this would alternate, you get beta x to the 6th over 6 factorial, dot, dot, dot. And if you recognize this thing, that is your Maclaurin series for cosine of x, or in this case, cosine of beta x. Okay? Then we've got plus, and we want to add all the ones that have the i's in them. I'm going to factor out the I. So here we're going to get beta x. And over here we get minus, I factored out the I, so beta x over 3 factorial, beta x cubed over 3 factorial, then plus this one, beta x to the 5th over 5 factorial, minus, and then dot, dot, dot. Well, hopefully you recognize this as the Maclaurin series for sine of x, or sine of beta x. Okay, so what we get is e to the I beta x is equal to this. Now, when we do the other one, e to the negative I beta x, I'm not going to go through that entire thing, but what you're going to get is cosine beta x and then minus I sine beta x. Okay, so these two things, we're going to go back over here, okay, to this page, and this e to the I beta x, e to the I beta x, I'm going to replace with this thing. So we've got y is equal to c1, this stays the same, e to the alpha x, and this becomes cosine beta x plus I sine beta x, and I've got plus my c2 e to the